Okay, so there are a lot of terms in this title that we are going to slowly define throughout the talk. Not very slowly because we have 30 minutes, but let's start with the easiest among them, which is just algorithms, or a bit more particularly, algorithms in the case of restricted inputs. So for many different problems in many different areas, we know that if we assume anything or some certain conditions on the inputs, we can have faster algorithms. And I'm not even listing examples for such problems because I'm sure all of us have enough in mind. What I do want to list examples of are scenarios in which this is common. So anybody has any examples for scenarios in which you usually have faster algorithms for certain instances?
Metric PSP.
What was that?
Metric PSP. Metric PSP.
I can't hear from that far. Never mind.
Metric PSP. Metric PSP.
Okay, good. Metric PSP it was, hopefully. Maybe I'll just list some things myself because I can hear myself quite easily with two microphones. One thing that we usually have faster algorithms for are sparse inputs, when sparse can mean many different things. So sparse in a very weak notion can just mean not a lot of edges, but it can also mean something more global, like maximum degree that is a constant, or something that is more structural, like being planar, having low tree width, and so on. Another example of things we tend to have faster algorithms for are random input instances. For many problems, in average case, we can do at least slightly better. So the main objective of what we are going to talk about in the next 30 minutes or so is finding some generalization of input families that includes at least those two families, for which at least several problems inherently can be solved faster. Okay, and the family of inputs we are going to discuss are going to be something we will call almost regular inputs. In the case of graphs, being almost regular is going to mean that the average degree and the maximum degree are somewhat close to each other. So we would want the maximum degree to be at most some constant times the average degree. So for a graph, this will be almost regular. Good, and as I said, this includes at least the case of bounded degree graphs, the case of random graphs with a little footnote about what the density is, but it also includes a lot of graph families that we don't tend to have much faster algorithms for. So for example, regular graphs of any degree also fall into that category, or all very dense graphs, because if, for example, the number of edges is at least a constant times n squared, then both the average degree and the maximum degree are roughly linear, roughly n. And the type of results we will want to get are kind of black box results, meaning something like we have a certain problem. If I can solve this problem, for example, maximum independent set in time c to the n in the general case, then for almost regular input instances, I can solve it in c minus epsilon to the n time. So if we have such a result, we will call it a black box result, meaning that I don't care about what is the running time or what is the algorithm for the general case algorithm. As long as the input is of a certain form, I can have a faster algorithm. The other type of result we will also mention are white box results, meaning that I only compare myself to the current state of the art or the conjectured state of the art, but not to every possible running time. And the examples we are going to see will be maximum independent set and k-sat for the black box case and graph coloring for the white box case. All of these are examples of NP-complete problems and exact algorithms for them. I'm not going to say much about why do we care about those, but several people mentioned either fine-grained complexity in which this comes up a lot, and one other thing that I want to mention is a problem that is kind of in the intersection of complexity theory and cryptography, which is finding hard input distribution for NP-complete problems. So this is a very big open problem that we don't know much about. The question is, can you come up with any NP-complete problem and any distribution of inputs such that it is provably NP-hard to solve this problem for an average input out of this distribution? Many of the candidates we had along the year for hard distributions for such problems were average or just random instances, so random k-sat or random graphs for coloring, for example. So this type of result implies that those natural and symmetric distributions, at the very least, can't be the worst case for those problems. Because if you take a random graph or a random k-sat, then the degrees are going to be, the average degree and the maximum degree are going to be tightly related to each other. So what we are saying implies that you can do better than the general case. Okay, let's talk specifically about two of the results. First, let's talk about k-sat. So what is k-sat? You are given a Boolean formula. It is in KCNF form. You want to decide whether or not it is satisfiable. This is, of course, NP-complete. Sat in general is NP-complete. K-sat is NP-complete as long as k is at least 3. These are among the... So sat in general is the first thing we knew was NP-complete. K-sat was in the first paper of Karp about reductions within NP. So this is very classical results. For k equals 2, we can do it in polynomial time. So 2sat is polynomial as we know. But if we do want to solve sat exactly, then we can ask ourselves, what can we do? And for general sat, the answer is probably not much. So the best sat algorithms we have for the general case run roughly in the same time as enumerating over all possible solutions. So we can use some very clever algorithms to shave off sub-exponential factors, but nothing more than that, and even a lot of people conjecture that this is the best possible. So this is more or less the strong exponential time hypothesis that people are using in all of the conditional fine-grained complexity lower bounds. On the other end, for any fixed k, we can shave off something exponential when we are trying to solve k-sat. So for every constant k, there is a 2 minus epsilon that depends on k to the n algorithm that solves k-sat. One other thing I want to mention about k-sat is something called the Sparsification Lemma. This is a result of Impagliazzo, Paturi, and Zain from the same paper in which they defined ETH and SETH. And it is actually something that is used a lot in all of the SETH lower bounds. This is the following statement. They show that for every fixed k and epsilon, you can take an instance of k-sat, a KCNF formula, and translate it to 2 to the epsilon n KCNF formulas, such that each of those formulas is sparse. Each of those formulas has the same number of variables as the original formula, but the number of clauses will be something linear in n. The constant will depend on both k and epsilon. So this basically means that if I want to solve k-sat in general, it is enough up to some price of 2 to the epsilon n, where epsilon is a constant as small as I wish, to solve k-sat only on sparse instances. So this is useful, for example, because then in all of the SETH lower bounds, you can assume that your instance is also sparse, that the number of clauses is linear. What our work implies is some either strengthening or a complement statement to this statement, which is the following thing. Basically, what we would want to say is that if you are starting with a KCNF formula that is not very sparse, that is slightly dense, then in fact you can do strictly better than the general case of solving k-sat. So we're going to show the following thing. If you can solve general k-sat in c to the n time for any c, then if I give you a k-sat instance that has at least some constant times n number of clauses, then you can solve it in c minus epsilon to the n time for some positive epsilon. And there is a small footnote. The small footnote is that you can't add clauses in a ridiculous manner, meaning that, first of all, we don't allow multiplicity. Second of all, you still need to have as many clauses as we stated here if I remove a negligible fraction of variables. So you can't do something like add root n variables and all possible clauses on them. But if you still have many clauses after removing any negligible portion of the vertices and you don't allow multiplicity, then this is true. Anything that is dense can be strictly solved faster than the general case. Good. The second result I want to talk about is for graph coloring. So again, a quick reminder of what is graph coloring. We have a graph. We say that it is k-colorable if you can assign colors or numbers between 1 to k, if we are talking about a k-coloring, to all of the vertices, such that no edge is monochromatic. No edge connects to things that were colored by the same color. Then this graph is k-colorable. in the coloring problem or the chromatic number problem, we are given a graph and we need to compute the smallest k for which the graph is k colorable.
Quick question.
Yes?
So does your result condition, like for k-sat, does it conditionally imply that something similar to a sparsification lemma? Because a sparsification lemma says give me any instance, I can make it a sparse.
Yes.
If I assume a strong ETH, then it means, and your result now, does it mean that the only hard instances are sparse instances?
Yes, with again a footnote of what is hard, because what we are saying is that you can shave off something exponential from it, but it could still be that dense instances are still exponential, just with a lower base to the exponent than the worst case of k-sat. Right, so it could be that sat in general takes 2 to the n, but for some reason on dense instances it's 1.99 to the n or something. Good. So a graph is k colorable if it's k colorable, and the problem of determining the chromatic number of a graph is NP complete. This is again from the same paper of Karp about reductions within NP, and also it behaves similarly to what we saw before in the sense that in the more restricted version, in which I give you a graph and a specific k, and just ask you to tell me whether or not this graph is k colorable for that k, then this is still NP complete as long as k is at least 3. So 3 coloring is NP complete. 2 coloring is just saying whether or not the graph is bipartite. This is a polynomial or even linear as well. On the other end, the naive running times of algorithms for coloring are not as easy to come up with as they are for SAT, or at least not as good as they are for SAT. Because if I want to k color a graph naively by trying all possible colorings, this will take me k to the n time. So this also depends on k. So for example, computing the chromatic number naively can take me n to the n time, which is a lot. But this is not necessary. So already in the mid-70s, Lawler came up with a very simple dynamic program that allows you to compute the chromatic number of a graph at 3 to the n time. So that people left exercises for the exercise sheet. So this is an exercise as well. If you want to solve it, one hint that will be useful for us, and I only mention this because this is something that will come up, is the following observation. A graph is k colorable if and only if we can take the vertex set and partition it to k independent sets. Right? Because in a proper coloring, every color class is an independent set. It doesn't contain any edge, but also every independent set can be colored with the same color, because again, it doesn't contain any edge within it. Good, and this was improved many, many times afterwards, until in the end, people reached something that before that, and still now, people think should be optimal for graph coloring, even though we have no formal reasoning of that, which is an algorithm that runs in 2 to the n time. So this is very similar to what we had in the SAT case. So currently it is known, and this is not trivial or not completely trivial at least, to find the chromatic number of a graph in 2 to the n time. So the next question should be, can we still do better if k is fixed? So can we do faster than 2 to the n for k coloring for any constant k? And unfortunately here we don't really know it. So we know how to do k coloring faster than 2 to the n for 3 and 4. This was known for at least 15 or almost 20 years ago. Actually, those results for 3 coloring and 4 coloring are a bit stronger. They also show that you can solve list coloring, which I will not talk about, but if you know it, it's a stronger problem than k coloring. And then recently, we showed that you can reduce k coloring to k minus 2 list coloring. So this means that those algorithms for 3 and 4 list coloring also imply better than 2 to the n algorithms for 5 and 6 coloring. But for k that is larger than 6, we currently don't know if you can solve coloring faster than you can compute the chromatic number or not, besides one very special case. So the only case in which we know that for every k you can do better than 2 to the n is the case of sparse graphs, or at least some general variant of what sparsity means. So if you have at least constant fraction of your vertices with degrees bounded by a constant, then you can compute the chromatic number exponentially faster than 2 to the n. You don't need to read this thing. The only corollary that we will care about is that it means that for sparse graphs, you have a faster algorithm. And in particular, if all of the degrees are bounded by a constant, then there is some epsilon, such that I can solve k coloring in 2 minus epsilon to the n, or even compute the chromatic number in that time. So this will come up. And in this work, what we are showing is that if my graph is almost regular in the sense that we defined, then we can improve over 2 to the n. So for every k and c, we can solve k coloring in 2 minus epsilon to the n time, as long as the average degree, as long as the maximum degree is at most c times the average degree. So as long as c is a constant and k is a constant, this thing is epsilon is a constant as well. And as we said before, this includes things like regular graphs and also all very dense graphs. Good. Any questions so far? Yes. Yes. So here epsilon depends on both k and on c. So this is true for a fixed k and fixed difference between the max and average degree. Anything else? Yes.
In the previous slide, what was the sparse? How is a sparse network defined?
That definition of sparse over there.
There.
This definition of sparse means that epsilon is a constant as long as m over n is a constant.
So
Right, because
so linear growth. So the number of edges is linear in number of nodes.
Yes, and this is just because of the slide that I told you not to read, which is that if a constant fraction of the vertices have constant degrees, you are fine. And if the average degree is a constant, then obviously half of the vertices have at most twice that degree. Okay. Good. So for the rest of the talk, what I want to discuss is the main tool we are using, which is something called the hypergraph container method, which is some relatively new, very, very powerful tool that was introduced in extremal combinatorics about 10 or 15 years ago. So it was introduced independently by both Saxton and Thomason and by Balog, Morris, and Samotti. Since then, it was used for many, many results in extremal graph theory, extremal combinatorics, additive combinatorics, and so on. A few more background words about this. So actually, in hindsight, it appeared that the same method for graphs rather than hypergraphs appeared much beforehand. It was not framed in the same method, but similar tools were used in previous works, but then again, only for graphs, not for hypergraphs. But they were the first one that showed it for hypergraphs, and this was very important. We will soon talk about why moving from graphs to hypergraphs is very meaningful. So what is this hypergraph container method? So this is basically the following statement. This is some characterization of how can the family of independent sets look like in a nice hypergraph. So nice would mean symmetric in some way. But we want to say something like, if I have a symmetric enough hypergraph, then it can't be that the collection of independent sets is completely arbitrary. What is an independent set in a hypergraph? This is just a set of vertices that doesn't contain a full edge or a full hyperedge. Okay, so let's try to say it gradually more and more formally. So we're going to say that if a hypergraph H satisfies some conditions, then the independent sets are clustered in some manner. So they need to be partitioned. So all of the independent sets can be partitioned to a few sets such that in each set the independent sets are similar to each other. And still not formally, but a bit more formally, what we are going to see is the following statement. If H is a nice hypergraph, which I still don't define, then there are containers. Those are just subsets of the vertex set. So we have subsets C1 to CR of the vertex set of the hypergraph, such that the following three things hold. First of all, the number of containers is small, so we don't have many of those subsets. Second, each container is not very large, so the size of each container is bounded away from the size of the graph. Each container contains at most some constant fraction of the vertices in the graph. And third, which is why they're called containers, each independent set in the hypergraph is fully contained in one of the containers. let's see some drawing. It's a terrible drawing because I don't have that ability. It's also a graph and not a hypergraph. But this is a graph. These are maybe containers for the graph. What would that mean? It would mean, first of all, that there aren't many of them. 3 is not a lot. Each of them is not very large in the sense that there are a lot of things out of it. There is at least a constant fraction of the graph that is out of it. And nevertheless, whenever you pick an independent set in the graph, it will be fully contained in one of the containers. So the way to think about it is that in each container, all of the independent sets are similar to each other because they are sharing vertices in some way. So there are a few templates. Those are the containers for what an independent set can look like. Good, and let's try to make this a bit more rigorous, but not for hypergraphs, but for graphs. So for graphs, we can state the full statement. For graphs, it will be something like, if G is a graph, it has n vertices. Its average degree is D. And the maximum degree is at most C times D. So it is almost regular in the sense that we mentioned before. Then we have this family of containers with the following conditions on them. First of all, the number of containers is 2 to the little o of n. But I am cheating a little bit because this little o is not going to be on the basis of n, but on the basis of d. So this means that this little o of n is going to grow to a, like this term over n is going to go to 0 when d goes to infinity, not when n goes to infinity. So if the average degree is super constant, this is actually little o of n. But if the average degree is just a large constant, then you should think of this as 2 to the epsilon times n. So for every epsilon, there is a large enough constant d for which this will be at most 2 to the epsilon n. The second thing is that the size of the containers is bounded away from the size of the graph. And this epsilon only depends on c. So if this c is a constant, then it is actually a constant fraction of the number of vertices in the graph. This does not depend on n or on d or anything like this. And actually, I will not have enough time to discuss this. You are very welcome to ask this in the question part or afterwards. But in many, many, many applications of the container method, this can be really improved. So what's written here can be something that is not close to 1, but a much smaller constant than this. And the third thing holds as before. So every independent set is fully contained in one of the containers. Any questions about the statement itself? Yes?
Sorry, I guess this 2 to the little OD and then is a little unintuitive. Is it true that it can be bounded by it's larger than some polynomial or super polynomial in n, or is it?
Think of this as 2 to the n over d. Maybe this is what you should think. It's not exactly, but roughly. Yes?
Does this actually mean that like if you take two verses in two different clusters, they have to have an edge between them?
What? Can you repeat that?
So I'm just trying to practice for myself. Like, does this mean that if you take two verses that are in two different clusters,
Yes.
that they should not belong to any independent set? Does that mean that they have to have an edge between them? Is the same? Or?
So it doesn't mean it could be and even must be that the containers overlap each other. So you can have edges between different vertices. This is not a partition of the vertex set. This is just some short list of templates of what an independent set can look like. So every independent set will be in one of those. Anything else? Good. So let's continue. And the next thing that I wanted to say is, why do we care about independent sets in hypergraphs? And the important observation, and this is not a very formal statement, but this is true for many, many things, is that every property that you can describe by forbidden substructures or small forbidden substructures, you can describe as being an independent set in some hypergraph. So let's see an example of that. So let's consider the hypergraph that is a 3 uniform. Every edge will contain 3 vertices, such that the vertex set will correspond to all possible edges of Kn. So I have a vertex for every pair of indices between 1 and n. I think of this as an edge of the complete graph with n vertices. And I'm going to add a 3 edge to my hypergraph for every triplet of vertices that correspond to a triangle. So every triplet of vertices that correspond to 3 edges that form a triangle, I will have some 3 hyperedge surrounding them. So now what are the subsets of vertices in this graph? there is a one-to-one correspondence between subsets of vertices here to all graphs on n vertices, right? Because a subset of the vertices of these hypergraphs is just a collection of edges in Kn. So the subsets of vertices are exactly all graph of size n, and the independent sets are exactly the triangle-free graphs, because being an independent set exactly means that you don't contain a full triangle. So for example, the hypergraph container lemma was used a lot to count things like this. How many triangle-free graphs do I have? What is the largest triangle-free graph that I expect seeing in GNP? And so on. And there was nothing interesting about triangle in that statement. You can replace this with any constant size structure that you are trying to avoid. But you can also think about this in contexts that are not graphs. So for example, if the vertices of my hypergraph are numbers between 1 to n, and I add a k hyperedge for every k arithmetic progression, then independent sets are going to be exactly the k arithmetic progression free sets, and so on. So as long as your property can be described by forbidden small substructures, you can probably describe yourselves as an independent set in some hypergraph. And what we are doing in this work is taking that work on containers and showing that you can algorithmically apply it. Actually, we need to generalize them a bit before that, but let's not talk about it now. Let's start by sketching the simplest way we can think of to apply containers. So what would be the easiest thing to apply it for is to apply it for a problem that involves independent sets. So let's start by talking about maximum independent set. Let's say that I have a graph for which I have good containers, so it is almost regular, and I want to solve maximum independent set for it. What could I do if I would tell you that somehow you can create those containers computationally? You could just create the containers, enumerate over them, and for each container, solve maximum independent set in the induced subgraph over the container. This is going to work. Why is this going to work? Because the maximum independent set is an independent set, so it will be fully contained in one of the containers. And on the other end, every independent set in an induced subgraph is an independent set in the entire graph. So the maximum of all of those things is going to be exactly the maximum independent set in the graph. And how much time does it take? So this takes the number of containers times how much it took me to solve maximum independent set for a general graph, but now not of size n, but of size that is smaller than n. So if we are not saying anything better, then for now just think of this as 1 minus epsilon times n. But you can actually improve this to be something like n over 2 or so on. So what you would get is that if you can solve maximum independent set in c to the n time, then you can solve it in a faster time for, say, a deregular or an almost deregular graph. But what we do need to notice is that we still have some term that depends on the degree. So if the degree is small, we are actually still not gaining much. We are still paying until the degree becomes high, which means, and this will be also the case in other scenarios, that containers give us an improved algorithm for almost regular graphs as long as the average degree is high. What is high? It is at least higher than some constant. Then what we are going to do usually is to combine it with algorithms for the bounded degree case. Right, so if we have a faster algorithm for the bounded degree case, for example, we saw one for graph coloring, then the combination of the two would give us an improvement in general. Good, so this is the recipe that we have in general, and the last thing I am going to mention is that actually this simple example is not going to work for other problems, because the problem will be that in most of the things we are reducing to independent sets, we will care about more than one independent set at the same time. So something that containers guaranteed for us is that every particular independent set will be fully contained in a container. But if I have a problem, say, graph coloring, in which I care about partitioning my graph to k independent sets, or any other problem that I reduce to some question about independent sets that involves more than one independent set at the same time, it will never work to just restrict myself to subgraphs. I do need to look at the entire graph. I do need to look at all of the, at several independent sets in the same time. And this can't actually work. We couldn't hope to have a container statement that would work for several independent sets at the same time, because if we keep the coloring example in mind, then it's quite trivial to construct graphs for which two independent sets cover everything. So if I would want something that sounds like the container method, in which every pair of independent sets is fully contained in a container, then I wouldn't be able to do it, because there are pairs of independent sets that cover the entire graph. So what we are able to show is that actually this is the worst that can happen. So we show some generalization of the hypergraph containers called partition containers, showing that you can get exactly the same guarantees, but now for every collection of independent sets, you would have exactly two containers, such that each of those independent sets is fully contained in one of them. So two containers are always enough to cover a collection of independent sets. So we'll have two fixed containers, such that every independent set among this K will be either fully contained in the first container or fully contained in the second container. I can partition those K independent sets to two parts such that each of them is fully contained in one container. And I'm not telling you why, but this is enough to improve all of the other algorithms as well. One reason to maybe keep in mind is that for some reason that we can't give really a formal explanation for, when I parameterize all of those NP-complete problems, if the parameter is 2, they are easy to solve. So 2 coloring is easy, 2 sat is easy, which means by some voodoo that if I have only 2 containers, then it is easy to solve. If I had more than them, it would not be true. OK, let's summarize. So we looked at this very powerful tool from extremal combinatorics. What we are sketching here is that it can be imported to the world of algorithms. We can also use it here. It shows that some problems are inherently easier on nice inputs, that if the inputs are symmetric, then you can inherently do better regardless of what is your algorithm for the general case. Something else that at least sounds good that we get out of this is that some constraint satisfaction problems, for example, SAT and graph coloring, do behave nicer when you have a lot of constraints. So something like solving graph coloring on a very dense graph. It sounds like it should be better, right? Because if I give you more constraints, then hopefully you should be able to solve the algorithmic problem faster. We didn't have any formal reasoning for that before. Now we finally do. But we do leave more than a few open problems here. The first of them is, can you apply this method for more things in computer science? Hopefully not for only exponential time algorithms. Meaning, can you use those containers in the analysis of things without explicitly constructing them? So in the combinatorics literature, they were used a lot to analyze the randomized processes. So maybe they can be used to analyze the randomized algorithms without explicitly having to build those containers. One more particular problem that is left open is, can you do K coloring faster than 2 to the n for every fixed K, which we now know how to do for sparse graphs and for dense graphs and for regular graphs. So maybe you should just finish it off with all graphs. Thank you very much for listening.
Questions?
Yes.
How fast can you compile these containers? Is it exponential time too, or?
Good. So actually, what you are able to do is to show that given a graph and an index of a container, you have a polynomial time algorithm that returns this index of a container. So you can enumerate containers in polynomial time times how many containers you want.
So I'm just curious, like in K-colorable problem, what makes it difficult to extend like K equals 6 to K greater than 6?
Good. So something that happens both in the algorithms for K coloring for the very small values like 3 and 4 and in the K-SAT algorithms for small values of K is that you are just trying to build a coloring. So you are locally trying to color a vertex, then you hopefully know that some adjacent vertices can't be colored with the same color, so it is a bit easier to color things locally. So you do clever local tricks and hope to get a coloring. What happens in the algorithm of computing the chromatic number is much more global. So you look at some algebraic property of the entire graph and try to find a chromatic number. And because the running time of the naive enumeration in K coloring grows with K, so it is K to the n, then your starting point for the local algorithms gets worse and worse. So at some point, they just become worse than the global thing. Yes?
You know, this dual problem of given a graph find its the smallest container partition, is that problem? I give you graph G, I tell you my one size of each of my containers with 1 minus epsilon n. I'll ask you what is the smallest number of container you need. Is that a problem we can, I don't know even if it's in NP or not, but is it something we can solve somehow or approximate?
I didn't think of that. The number of containers is still quite large, so it's definitely not in, I mean, it's not in P for stupid reasons, right? Just because the number of containers can be exponential or close to exponential if the degree is not small. Yes. No, so it's not clear how you would be able to find the smallest number of containers. Yes,
and for a typical graph, is it that like almost every graph that you work with requires exponential in any container?
So the example to keep in mind is that if you fix some degree d and take a random graph in which the average degree is d, then you don't expect seeing any independent set of size much larger than n over d. So their possible containers would just be all subsets of vertices of size n over d, right? Because there aren't too many of them, and each independent set is just one of the containers. So the container method is basically saying that even though your graph is not random, still for some structural reasons you can get the same number of containers. Of course, they will be larger because an independent set can be larger.
I have one soft question about this. How did this come about? Like, were you saying, here's a tool called containers, how can we apply it? Yes. Were you saying, here's okay.
Wojtek is in Tel Aviv University since about 10 years ago. He keeps talking about containers, obviously. He does a lot of amazing stuff with containers in combinatorics. It was annoying that you have this fancy hammer that all of the people in the other side of the corridor are using, and we didn't manage to use it yet for anything.
Okay, let's thank Or again.
Thank all of you.